Anytime you're ready, Alan.
Well, welcome everyone. This is Alan Taub. I am the director of our Electric Vehicle Center at the University of Michigan, and really pleased to have everyone join for our Surge session webinar for the month of May. It's on transforming mobility with autonomous electric vehicles, and it's a report out on a project that we actually sponsored with the Electric Vehicle Center that was first suggested by Larry Burns. I mean, Larry, I've known for over 20 years. He is the person who brought me into GM. And what was interesting, because I joined in 2001, by that time, Larry had already envisioned what we called the reinvention of the vehicle: autonomous, electric, connected, and shared. And it took 2 decades, but we have achieved that. I mean, those vehicles are now on the road and becoming commonplace. So clearly, someone like Larry then had to go to the next step. Well, how does that change mobility? And with a concentration right now on mobility in urban areas. And so what you'll see is some comments from Larry and a presentation by Professor Saif Benjaafar. He's a professor at U of M in the IOE department, but also co-director of the Tauber Institute for Global Operations. And he brings long experience in shared mobility and sustainable operations. We'll also hear from two of his students, Jingyuan Wan, who's a PhD candidate, and Bhavye Mathur, a U of M undergraduate. So with that, what we'll remind people of is at these webinars, we ask you to hold your questions until the end. You can post them in chat during the meeting, and then Jamie Ratcliffe, our communications director, will facilitate a question answer session at the end. Also, a reminder that this webinar is recorded and available on our website. So with that, let me turn it over to Larry.
Thank you very much, Alan. And thank you very much for the EV Center at University of Michigan sponsoring this research. Alan invited me to give the keynote for the Center Symposium a year ago in April. And this research grew out of that presentation. A colleague of ours, Bob Bordley, introduced me to Saif, and Saif and I reached an agreement that we thought we could do something significant here with what we call a digital twin or a simulation platform. And he brought along two extraordinary students who have shown a lot of initiative and resolve to get us in the position we're in today. Saif is going to run the show. I'm going to come back at the end and put the results that we show in the context of that longer research theme that Alan was talking about. Saif?
Right. Thank you, Larry. And thank you, Alan, for hosting us today, but also for supporting this pilot project. So maybe a bit of context. Let's see. Bhavye, if you can share our slides. I don't know if Bhavye should be online.
The slides should be shared. Can you?
I do not see the slides. I don't know. Is it just me?
I can't see them either. Saif.
It says there's an issue with content sharing. Try again. Jingyuan, if you have the backup, could you?
Yeah, I have one. Maybe I can try. Everyone.
Yeah, if you can go in presentation
okay.
mode, please.
Okay. Sure.
There we go.
Okay.
Okay. All right. So maybe yeah. So that's the team. Maybe the next slide. So a bit of context. So the current model of mobility, right, as both Alan and Larry alluded to, of privately owned vehicles is very inefficient. So cars sit idle about 95% of the time, occupying valuable space, depreciating in value. A majority of trips are also short distances and involve one or two people. And so if you think about seat utilization rather than car utilization, then that utilization is less than 2%. AV technology is maturing. Real-world deployment is happening here in the US and elsewhere. Waymo now operates in multiple cities and has logged millions of paid trips. We're seeing similar deployments in China. I was there last December and was just got a chance to experience an AV service. We ride in China. It's pretty impressive. And other parts of the world, Middle East, Europe. EVs also becoming cheaper and range continues to be extended. The EV center is certainly playing a big role in that space. And then on-demand mobility, that is one way. Free floating is now a proven concept. So perhaps time now starts to take more boldly. Larry has done this for decades about the mobility future that is mostly on-demand, shared, autonomous, and electric. So what we're going to do today is share with you some preliminary results from this pilot. Share with you sort of baseline findings using this digital twin that we have developed that is data-driven with data provided with data for Southeast Michigan, including Ann Arbor, kindly provided by SEMCOG. So at the risk of stealing our own thunder, let me share with you the bottom line from these preliminary findings. So for communities like Ann Arbor, autonomous electric robo-taxis can fulfill, this is the finding, this is a preliminary finding, can fulfill nearly all car trips with just 15% of current vehicles and a mean pickup time of less than 4 minutes with pretty high reliability. So the 90th percentile is about 8 minutes. There are all kinds of implications of deploying autonomous vehicles at scale, including for parking. And we have done some preliminary analysis for parking and find that parking requirements for a city like Ann Arbor can be reduced by about 90%. So Ann Arbor has about 150,000 spots. This could be reduced to about 11,000 spots. Okay, so next I'm going to turn it over to Jingyuan, who will walk you through the data that we have used. And then Bhavye, he will walk you through the simulator, okay? And then we'll come back to the findings.
Okay, sure. Thanks, Saif. So let me first introduce the Southeast Michigan region that we started in this work. So this map shows how this region looks like. And with these 7 counties and 4.8 million people, this region contains cities and townships in different sizes. And for instance, we have Detroit, a big metropolis area, Ann Arbor, a college town, and also other small towns and rural areas. So it really provides a large variety of instances for our testing of autonomous vehicle sharing services. So the main data set we use is this detailed origin destination trip data obtained from the Southeast Michigan Council of Governments, or SIMCOG. The data is collected from multiple resources, including mobile signal data, onboard federal census information. And here is a snapshot of the data set. So each row contains a pair of origin zone and destination zone, the time of the day being either morning, afternoon, evening, or night. The weekly type being either weekday or Saturday or Sunday. And also we got the distance in mile and also the number of daily trips, which is an average of a year. And the data set we have contains over 1 million rows that represent a total of 81 million weekly trips in the Southeast Michigan region. And we use this data to sample customers' trip requests in our simulation. And for the time and distance of each trip, we use Google Maps to get an estimate. Some key characteristics of the trip data. First, the scale is enormous. There are, on average, 13.5 million trips per day corresponding to approximately 265 million person mile traveled per day. And if we break down the data in different ways, we see the heterogeneity of the number of trips in the time of the day, the trip length, and also the occupancy. And the one thing I want to highlight here is that the average occupancy is only 1.9, which means on average, there are going to be around 3 empty seats during each trip if we assume most of the cars we currently use are 5-seaters. So this suggests a huge opportunity to improve the utilization of our seats. But even before that, another striking observation from the data is that cars are highly underutilized today. The left figure shows that even during the peak hours, there are fewer than 350,000 vehicles in use. And compared with the 3.7 million registered cars in the Southeast Michigan, utilization is less than 10% at any moment. And in other words, most vehicles spend most of their time parked and idle. So again, huge opportunity to improve the utilization. And this analysis shows the big potential value of autonomous shared mobility systems, where a highly utilized vehicle fleet could potentially satisfy the same transportation demand with fewer vehicles, fewer seats, and less parking spots needed. So here is some beautiful animation showing the trips in Southeast Michigan, and this is credit to Bhavye. So I'm now going to turn it over to Bhavye.
Yeah, so here is an example of the kinds of trips that we can use the data to generate. We're looking at a region surrounding Detroit right now. And in blue, we've got trips that are moving into Detroit. And in red, we've got trips that are moving out of Detroit. So as you move to the next slide, you kind of see the trip and the patterns changing over time. So you can see that we can capture the temporal effects of commuters, so people coming in and leaving the city, and all kinds of other really nice and interesting effects in our data. So this really helps us simulate and make a digital twin that's an accurate representation of the world around us. Now I'll talk a bit about the simulation platform itself. So you've seen the trip data. Now combined with that, we have come up with various kinds of policies to match vehicles to customers and to perform things like charging, because vehicles, we're simulating electric vehicles and they need to be charged. We are simulating things like repositioning. And so we basically have a variety of policies along with the trip data that are fed into the digital twin. And this digital twin is basically a high-performance simulation engine that is responsible for simulating tens of thousands of vehicles and potentially hundreds of thousands of trips or millions in the matter of minutes. And from it, we get a performance assessment of everything that's going on. So we are able to figure out how long customers have to wait for a vehicle to arrive. That's called the response time. We're able to figure out the service level. That's the number of customers as a percentage that we were able to serve, and basically all kinds of really fine-grained statistics. Now, I'm happy to talk about the simulation engine itself. This is sort of what goes on under the hood. This is really more of a computer science thing. We've basically spent a lot of time engineering this to be as fast as possible. So like I said, we're able to do tens of thousands of vehicles and potentially millions of requests in the matter of a few minutes. So yeah, we won't spend too long on this. But the goal of using the simulation and of using all this data was to answer the question, let's talk about the simulation dynamics. So Jingyuan,
yeah, maybe turn it over to Jingyuan, who will talk a little bit about sort of the dynamics of operating an AV fleet. And this is what is being captured by the simulation.
Yeah, sure. So yeah, I'm now going to introduce the model dynamics in our simulation. So here is a stylized illustration of the service region where we have vehicles circulating and the multiple chargers are built here. So vehicles can be in different status, either serving on some trip request, on its way picking up some customers, or going to chargers, or in charge, or just stay idle. And during the simulation, we also keep track of the status of each vehicle including its location, its charge level, and whether it is moving or not. So here is what's going on in the system when we simulate. At some time, a customer arrives and requests a ride. And then some matching algorithm searches all the vehicles within some radius and determine which vehicle to dispatch to this customer. And let's say this vehicle is chosen to serve this customer. And then it moves to the customer, pick up the customer and drive the customer to its destination. And then the vehicle drops off the customer leaves the system, and the vehicle status is updated. And finally, another algorithm will decide on the next step of the vehicles, whether it could be repositioned to somewhere else, or go to a charger if the charge level becomes low, or just stay put. And all of these events will occur repeatedly in our simulation. Okay. Yeah, and then I'm going to turn it over to Bhavye to illustrate this animation again.
So here we've got a visualization of the dynamics of the simulator and all the vehicles that we're simulating in the Washtenaw region. So here you can see in blue are the autonomous vehicles that are moving all around the simulation region, and they're servicing customers, picking them up, dropping them off. And red is an experiment with repositioning. So this is where we're moving vehicles from areas of lower demand to areas of higher demand. And this is exactly the sort of fine-grained, high-resolution simulation that our digital twin is performing. And all of this is in an effort to answer the question on the next slide, which is how many autonomous vehicles do we need to satisfy nearly all of the demand with a mean response time of less than 4 minutes? And so sort of in this vein, we're trying to achieve very reasonable tailed response times as well. So as a case study, let's consider Ann Arbor. This is home to around 125,000 people. Most of them are students. It's an area of around 30 square miles, and we observe about 4 million trips per week. So that's the region we're simulating. We also sort of crop our trips to the region, so trips that are entering and exiting the region according to the entryways on the next slide. So along the Ann Arbor loop, we've got 19 over or underpasses or expressway exchanges. So when we have trip data for all of Southeast Michigan, we essentially crop that trip data to the Ann Arbor region, and we sort of move these trips to basically be entering or exiting from these 19 areas. So the next slide shows a little bit of what we're simulating. So we essentially sample these trips from the SEMCOG data that we mentioned earlier. So these are samples of origin destinations for different times of day and different days of the week. And those are samples from the distribution and then cropped to Ann Arbor. We simulate a policy where we've got 5-seater autonomous vehicles that must reach the customer within 15 minutes. And if no vehicles are able to reach the customer within 15 minutes, then we drop the request. And essentially, we assign the customer to the vehicle that can reach them the quickest. And we want to analyze how the fleet size, so this is the number of vehicles that we have, affects the fulfillment of demand, as well as how fast we're able to get the vehicle to the customer. That's the response time. As for charging, we've located 2 charging hubs within Ann Arbor. So they are located within the city. And whenever the charge level of the vehicle drops below 20%, we move the vehicle to a charging hub and then charge it until it's about 80% charged. That takes about 1 hour. And the range of the vehicle is around 300 kilometers in total, 200 and somewhere around 200 miles, I suppose. Okay. Yeah. Right. So here is an example of the data and of the cropping. So on the left, we've got data for all of Southeast Michigan, and we take this small slice just for Ann Arbor, which is what you've got on the right, and we clip the entry and exit of the trips to the 19 underpasses or expressways. All right. On the next slide, here is an animation of what some of these trips look like. So in blue, we've got trips that are entirely within Ann Arbor. So these begin and end in Ann Arbor. And in yellow or orange, we've got trips that are entering or exiting Ann Arbor. And so this is a video over time that just shows how the trips sort of go up during the afternoon, the evening, and come back down during the night. Okay, I'll hand it over to Professor Saif to talk about the results.
Okay. Hopefully you get a sense of the simulator, but also of the dynamics of the system we're trying to capture with the simulation. Drum roll here. So these are our preliminary results for the Ann Arbor setting. So what you're seeing here is a figure showing on the x-axis the number of vehicles. Okay, so this is the fleet size of autonomous vehicles. On the y-axis, on one side, it's response time. So this is how long it takes for a request from the time somebody places a request for a vehicle until the time the vehicle shows up. And then on the other side, the other y-axis shows the percentage of demand that gets fulfilled. Okay, and as you can see, with about 11,000 vehicles, we're able to hit a mean response time of less than 4 minutes, fulfill nearly all of the demand, almost 100% of the demand, and then be pretty reliable. So the 75th percentile is less than 5 minutes, and the 90th percentile is about 8 minutes. So compared to where we are today, this is the best estimate we have for the number of vehicles that are involved in fulfilling demand within the Ann Arbor region, into the Ann Arbor region, out of the Ann Arbor region, is about 80,000 plus vehicles. We can get away with about 11,000 vehicles, so about 15% total fleet size. Dramatic savings on number of vehicles. Next slide. This slide shows the status of vehicles over the course of a day and over the course of a week. Let's see. So on the x-axis is time, on the y-axis percentage of time where the vehicles is in particular status. So vehicles can be idle. That's the light blue. They can be charging. That's the yellow. They can be picking up a customer. That's the pink. They can be waiting for a customer to get into the vehicle. So within the simulation, we allow for a couple of minutes for somebody to get in. The dark blue is when you're dropping off a customer. There's a couple of minutes to allow for that transition, and then the I don't know, the navy blue, I suppose, is vehicles traveling from the origin of a trip to the destination. The things to highlight here is there's lots of interesting things to ponder here, but if you look at vehicle idleness, percentage of time vehicles are idle during daytime, it's about 20%. So there's very little slack, right, during the day, and then vehicle idleness across the entire time window of a week is about 50%, compared to the 5% we see today. So this got us thinking about sort of look at these implications, particularly for parking. Vehicles are on the road doing things more often, so there's a significant opportunity to reduce, right, the amount of built environment that's dedicated to parking, among other things. So next slide, Olivia. So we'll come back to the parking issue, but we should mention that what we're showing you is really a baseline case with not a lot of effort to kind of improve on the efficiency of the system. We believe that number, that 11,000, could be dropped in a significant way through improved customer matching algorithms. So the algorithm we use is kind of pretty simple, pretty myopic. By doing dynamic repositioning, by assessing where the demand is, where the supply is, and repositioning vehicles in a more dynamic way to match supply with demand. Smart charging. Right now, the assumption in the simulation is that when the charge level, the state of charge drops below 20%, that triggers a repositioning to depot to charge. One could be anticipatory, and during off-peak periods, you could charge vehicles even though the state of charge is not below that threshold. And then there could be opportunities involving ride pooling. So a small, perhaps, segment of the population will be able to share rides, willing to share rides. And then the even bigger opportunity is if we rethink the design of vehicles. So thinking about purpose-built vehicles, something we'll come back to toward the end. Here's a kind of very first order assessment of the implication on parking. Today, there's about 100 within the Ann Arbor area, 150,000 parking spots. 6% of total land area is devoted to parking. Significant investment associated with parking. These initial results we have suggest that you could get away with about 3,500 parking spots within the city. So because that 20%, the number of vehicles or the percentage of vehicles that are idle is about 20% of the fleet. And then 11,000 parking spots at night. So that could be within the charging depots or in areas outside the city. Okay, next slide. Okay, all right. So, okay, let's see. So okay, so key takeaways for communities like Ann Arbor: autonomous electric robo-taxis at scale can fulfill this first order estimate, right? Fulfill nearly all car trips with just 15% of current vehicles with a mean pickup time of less than 4 minutes, with pretty high reliability, and then this opportunity for parking. Next slide. Okay, I mentioned there's potentially an even greater opportunity. So beyond autonomy, beyond sharing, beyond on-demand, purpose-built vehicles. So this is really a passion. Larry is very passionate about vehicles tailored to trip requirements, right? And the data suggests that the biggest chunk of trips are short and involve few people, 1 or 2 people. So why are we moving around tons of steel and many seats? So next slide. There's perhaps an opportunity to redesign the car for the AV era. This is already happening. So potentially a big chunk of the demand could be fulfilled by smaller vehicles, right? The 2-seaters, for example, right? Taking care of that 80% of the demand, 4-seaters, and then larger vehicles for larger trips, family trips, and so on. There's a lot of interesting in terms of the simulation. There's lots of interesting algorithmic issues of how now do you manage a mixed fleet of different sizes? How do you dispatch, for example, trips involving 3 or more people? You could still use the 2 vehicles by dispatching 2 vehicles of smaller size, like 2-seaters, 2-seaters. That's a replacement for a 4-seater, and so on. So there's like those kind of economies could be realized. Next slide. This is the beginning. So we're hopefully we gave you a sense of what the kind of questions we're trying to answer, and then the kind of tech we're leveraging to come up with these answers and these estimates. We would like to enhance the capabilities of the simulation by increasing kind of granularity of what we're modeling, road network, congestion, traffic. We'd like to dig deeper into these implications for parking in the built environment, and then come up with better estimates for the economics of mobility, cost models for autonomous EVs when they're deployed at scale, and then extending the analysis to other communities in Michigan and beyond. Next slide. think this is, yeah. So we'll stop here. Again, really grateful. I am personally grateful to Bob Bradley for putting me in touch with Larry, and then for Alan for supporting this this kind of visionary idea of thinking about what this what the AVs when they're deployed at scale, how they can be transformative to how we fulfill mobility needs. And we're also very grateful to Semcog, who's been very kind sharing their data, but also interacting with us, answering lots of questions. Okay.
So
Next slide.
Yeah, Saif, I think I was going to make a couple comments at this point.
Yes, yeah. I'm going to turn it over to Larry.
You know, to help you understand the significance of the initial results, I want you to consider two ways to fulfill the travel demand in Ann Arbor. So just sort of put yourself in this hypothetical world. The first is to replicate the current system that we have, which is a personal auto-centric system. This would entail buying 80,000 cars at $50,000 each, which is the median price of a car today, which is $4 billion of investment. It also involved buying about 1,200 acres of land at $500,000 an acre for about a $600 million investment in land for parking. The people who would use this system would need to spend their time driving. They'd have to look for parking. They'd have to walk to their final destination from their parking spot. The cars, as Saif indicated, would be parked 95% of the time, and when they're being used, 3 of the seats would be empty. This means there would be about 390,000 empty seats in Ann Arbor at any point in time, which is about 3 times the size of the U of M football stadium. There would be about 7 million kilowatt hours of battery sitting around idle most of the time. Now, the second opportunity would be to embrace autonomous electric vehicles at scale as robo-taxis. And as the research indicates, we need 11,000 5-seat vehicles to do this. The Waymo Ojai, which was the vehicle on the right on the slide Saif just shared, estimates are that it's about $125,000 all in, vehicle, sensors, and other things. So this would be a $1.4 billion investment, 65% less investment than buying all of those cars. Beyond that, you'd also need about $40 million for the land because we have to park these robo-taxis at night. Waymo and a company called Safe RE are indicating their vehicles are about 8 times safer than human-driven vehicles. This is safer for the people in the vehicle and the pedestrians. These robo-taxis would be idle about half the time, and their seats wouldn't be full all the time. So we'd have about 40,000 empty seats, which is 3 Chrysler Arenas worth of empty seats. So it's a huge opportunity. I really think it's obvious that the second option is where we would head if we could start with a clean sheet of paper. And it's going to become even better, as Saif mentioned, with the additional research we want to do. And I'm especially interested in this optimal mix between 2-seat vehicles and perhaps 4 or 6-seat vehicles to see what that fleet looks like. I want to emphasize we don't have to wait for this additional research to get moving on it. In fact, even if you're thinking maybe Larry's out over his skis a bit, you know, what's happened since I gave this symposium a year ago is that NVIDIA is all in on autonomous. They're creating an autonomous all-in platform. Amazon with Zoox, Alphabet with Waymo, Tesla. The market caps of those 4 companies alone are $14.6 trillion. They're committed to making this happen. Just a couple of weeks ago, a Chinese company called Leap Motor started leasing vehicles in Europe for a monthly lease price less than the cell phone lease price that Europeans pay. So low-cost electric vehicles are here. Autonomous vehicles are inevitable. You need to think about them together, not separately, and we need to move fast. Why do we need to move fast? The Strait of Hormuz, our oil dependence, the cost of a barrel of oil, the geopolitical dynamics around that. It's haunted me my entire career, and it's haunting me again today. We also need to move fast in the state of Michigan because the combined market caps at GM and Ford, you know, they're about $150 billion playing against $14 trillion players. And if our home team companies continue to harvest the legacy of a 100-year-old paradigm for big, heavy, powerful automobiles that stay parked 5% of the 95% of the time. I'm really, really concerned about their destiny. So the EV Center has given us a chance to get some additional insight. We appreciate your time because we believe common understanding of what's possible is a foundation for collective will. And we need to get that collective will in place sooner rather than later because this is such a compelling opportunity. So I'll stop there and we can open it up to Q&A, Jamie and Alan, however you want to facilitate that.
Well, first, let me thank the presenters for an outstanding presentation. And, last time, Larry, you and your team presented a vision within 20 years. We've achieved it. Let's see how fast we can move in this direction. So let's open for questions. Jamie, I'd ask you to facilitate that, please.
Yeah, guys, you can stop sharing your slides so we can see the answers better. Early on in the presentation, Harvey Bell asked, how can these vehicles be integrated into virtual power plants or VPPs to provide available stored energy to enable peak sharing?
Peak shaving,
Shaving.
You've got a lot of battery. You got a lot of battery capacity.
Yeah, I'll take that one on. I think it's an important question because I really think the opportunity for the world is to integrate our systems. So integrating our energy system with our transportation system and being able to manage our energy for industrial, residential, commercial, and transportation purposes is one integrated system makes a whole lot of sense. And I think it's all back to this temporal dimension. And I'm really glad Bhavye emphasized the temporal patterns of demand. And when we have excess electricity in these vehicles, but absolutely, I think there's an opportunity there.
Yeah. But shout out to some other research. Joanne Matthew, part of an EVC Center project, also looked at an integrated VPP vehicle system.
Nice.
All right, another question from Bernard. Did the baseline data come from SEMCOG, and is there a particular study or project that served as the source?
I think I can. Yeah, I can take this one. So based on our interaction with SIMCOG, I believe their data comes from some data sources. For example, Lucas is a provider of their original data. But then they do have some project that study those data, and because the original data is only represents around 10% of all trips, and then they, although we're not fully informed of all the details, but they certainly do some study to make that data to be representative for all the trips.
Yeah, a lot of the origin destination trips is cell phone data, is based on cell phone data.
Yeah, it's based on cell phone
provided
data.
by a third-party provider. This is our understanding from SEMCOG, representing about 10% of all trips. And then SEMCOG, along with the service provider, there's some extrapolation that happens to kind of scale it up to the true numbers.
Great. And Joel asked, have we looked for a sniff test via someone from Waymo or Lyft to sense check this approach and general findings?
So I am actually involved in a project with Waymo. So I'm working with the team that is doing similar kind of things within Waymo, developing algorithms, for example, for repositioning vehicles that is battery aware, designing the network, where to place charging hubs, and so on. And a lot of the assumptions we're using in the simulation are aligned, I would say. I mean, I cannot share specific data from Waymo, but they're aligned with how Waymo is thinking about the dynamics of the system, but also kind of some of the operational levers they have.
Good. And Andrew asks, are special events in Ann Arbor, such as graduation, move-in, or home football games, considered in this model?
I would not think they are, Jamie. I think those are going to be things we're going to have to handle. And you could conceive of people coming to the football game and robo-taxis from throughout the metropolitan area. I think those are scenarios we need to look at. That's always sort of been the bugaboo with this research area is people buy cars for their extreme occasional use, and then they use them for their typical everyday trips. And then there's extreme occasional events. And I'm not trying to be negative here. We just have to be careful about talking ourselves out of getting on with this because you can think of a but that we might not quite be able to handle. I think we'll find a way to solve those kinds of situations.
Yeah, in a way, autonomous vehicles that are on demand and shared solve this huge headache that happens during big events, right? How to get people to the stadium or to the event, where should cars get parked and so on. So that problem goes away completely.
And then Andrew also asked, is it assumed that a vehicle will only leave the charge hub once it's reached 80% charge?
Yeah, that's right. So we move vehicles to charging hubs basically around the time they hit 20%. So they might be completing a previous request, and then they charge until 80%.
But this is a good question. So when we mentioned that an area of future research is smart charging, that also involves kind of being opportunistic and dispatching vehicles when they're needed, right? If we see a surge in demand and we have vehicles getting charged, they haven't hit the 80% yet, but maybe they're sufficient. They have sufficient charge. Then you can also deploy them.
Yeah, and the nice thing about having a tool like this, the 80% sort of comes from, I would say, historical thinking that battery life, when you charge above 80%, begins to get compromised. Well, let the EV Center and your battery expertise tell us, and we can tell you how much being able to charge to 90% might be worth at the systems level. So this tool, I think, would give us some interesting insight on that question. How important is it?
Great. Joe asked, how are historical and daily traffic congestion conditions and effect on mean trip times modeled, and does it assume any modeled improvement based on reduced number of total vehicles due to more autonomous vehicles on the road?
Bhavye, do you want to take that one?
Let's see. Yeah, maybe the profile, the vehicle usage profile by VA is insightful for answering this question.
I believe Joe is also talking about the effect of, I suppose, traffic on the speeds at which the vehicles are moving. And I think, yeah, so for the moment, we assume that vehicles travel. Can you see my screen, by the way?
No.
Oh, you can't, okay. Jingyuan, you might have to share this.
Yeah, okay.
Sure. The vehicles travel at 25 miles per hour, which is an estimate of what vehicle speeds look like. But one of the immediate next steps that we're actually taking is trying to incorporate historical traffic and congestion data and the physical road network itself into the simulation. I think this will sort of have effects mostly during the peak hours, and where you'll see that at maximum we sort of have almost like 90% of vehicles that are currently en route. That's the red region plus the dark blue region at the top. That's about 10,000 vehicles or so. So it'll definitely have implications on traffic and congestion. I think something maybe Larry, you want to talk about this is the sort of increase in the throughput that's possible when we consider specialized vehicles. For example, if we consider two-seater vehicles that take up much less space, we might be able to use our roads to be able to send a lot more vehicles through it, just having profound implications for throughput of roads as well.
Yeah, I think this is another good question because it highlights the importance of having a digital twin of this type. We know, for example, congestion can result from today people looking for a place to park or pulling into a parking spot, trying to parallel park. But we could also argue robo-taxis could be congestion because they're pulling over to the curb to pick people up and drop people off, and that can add to the situation. We do have an opportunity if we get to two-person tailored design vehicles, they could be inline seating rather than side by side, which could give us more narrow vehicles. There's a lot of evidence to suggest that traffic flows more smoothly when you have all of the vehicles operating like with advanced adaptive cruise control, so we have those opportunities. But I think the devil's going to be in the detail on congestion, and I think a tool like this is going to help us get at that. I don't have a perfect answer right now.
Yeah. I mean, looking at that picture, right, reminds me of some work we did in the context of the power grid, and there are opportunities in managing electricity consumption, right, through what's called demand response. So we incentivize users to postpone maybe some of their usage, some of their consumption. So here too, right, this is an on-demand service, so one potentially could design incentives for users to delay some trips or reshuffle sequence of trips and so on, shaving off those peak periods, and therefore further reducing the total number of vehicles needed to support the same level of trip demand.
Yeah, I think that's an example of why being able to study this mix of vehicles is interesting, because the 6-seat trip is something that's sort of unusual. You might be more likely to schedule that. And I schedule a lot of my Uber trips to the airport. I reserve one in advance, and I know that helps Uber plan their day as well. And that's going to have fleet efficiencies. One thing I do want to emphasize, this is a really exciting opportunity to take this 11,000 5-seat vehicle example and make it even better. But it is so much better than personally owned automobiles when you have 80,000 of them today, that we need to get moving toward this shift, this transformational opportunity out there. Yeah, I mentioned this $125,000 cost estimate for Ojai. I don't think that's Waymo's internal number. I'm sure they haven't published it, but consultants have been modeling it, and they've come up with a number like that. Let's say, for the sake of simple math, the autonomous driving part of a future vehicle is $100,000, but the vehicle lasts 300,000 miles. That's 33 cents a mile for the driver. An Uber driver making $20 an hour, averaging 30 miles an hour, is double that. So we're already in the world of viability for this kind of autonomous electric vehicle system at scale. So I'm real excited about all these future refinements, but today's message also is we got to get on with a new future here, because the world we've lived in for the last century is just simply not going to work in the future.
Alan Hedgel shared a couple of thoughts that maybe one of you would like to comment on. I would love to see an accurate consideration in these efficiency models for the human-centered challenges that people with disabilities in our region face, and how sparse and underserving paratransit and wave mobility is. More than 28% of our regional population have disabilities, and most simply end up homebound and give up on mobility, especially as they age in place. Hopefully this is where you're going now in this segment, but there's significant concern from the disability community that at the national level, that Waymo, Zoox, and others today are ignoring the civil rights of riders in their launches in the name of progress.
Thanks for bringing that question up. I do find that interesting, because I was an advisor to Waymo for 11 years, and one of our first true riders was a blind person. And just for the purpose of this audience, I lived deaf entirely for a year. I have a sensitivity for people with disabilities. We have a great opportunity to serve this community because it's door to door. And we will find out with this digital twin just how big a fleet size needs to be for maybe more purpose-tailored vehicles for the physically immobile who need an assistance to get in. I was involved with the design of the Waymo Ojai. The flat floor and the door opening was intentional in order to accommodate wheelchairs, for example. So yes, it's a very important subject, but I don't agree with the conclusion that at least Waymo, who I worked with, is not dealing with this. Sergey Brin personally got involved in this because he has a relative with Parkinson's disease. So I think there's a passion to solve this challenge.
Joel asked, what do you think might happen with a very different city profile such as rural or a bigger city like Chicago or New York that have established mass transit?
Yeah, I did some research on this at Columbia, wrote a paper in 2013 with a colleague, Bill Jordan. And what we concluded at that time, and it was not nearly as sophisticated as what Saif, Bhavye, and Jingyuan have created here. Bill and I were using equations. But we concluded if population density is around 1,500 people per square mile, and Ann Arbor is closer to like 4,000, that this kind of robo-taxi service works. You still have sufficient scale on the demand for rides. But interestingly, in our preliminary work here, and the team weigh in on this, we do realize we have larger fleet requirements because part of the SIMCOG area is rural. And it's sort of one of these things, why do people rob banks? That's because that's where the money is. Robotaxi services are going to work well in suburbs. They may not work as well in rural areas. We might have to find some supplemental solutions for those areas.
Good.
I mean, the autonomy may solve the problem of labor, right? It's challenging to find drivers, right? The biggest chunk of the cost of operating a transit system are drivers, and in sparsely populated areas, you may not have the population of people who may be willing to drive. So, I mean, the cost may be higher, right? You may need to, relative to the size of the population, you may need a bigger fleet size, but there could be economies on the labor side.
Mark asks, he says, successfully managing safety is a key gate in unlocking this transformation. How have you seen advances in this area progressing, and how do you see that impacting adoption trajectory? Can adoption of existing driver assist features, such as Super Cruise, provide any indication of level 4 adoption?
Well, I think, first of all, as a robotaxi fleet, every time you learn how to make a robotaxi safer, you can put that safety enhancement into every vehicle. Every time I learn how to drive a little bit safer, I can't transfer my knowledge to Jamie or Alan or Saif and make them safer drivers. So this is the beauty of it. And you see situations recently. Waymo had a situation where one of their vehicles unoccupied went into some floodwaters, and they openly shared that fact, and they're using it as a learning opportunity so that that won't happen in the future. Human drivers still will make the mistake of going into floodwaters. And so I think the consistency we're going to get, and the Waymo data has really been studied inside out and upside down on how much safer they are relative to pedestrians, bicyclists, the severity of crashes, the frequency of crashes, and the risk of fatal crashes. So I think we're talking 5 to 10x. And I'm not sure humans are ever going to get over the hump. We've seemed to flatlined here at about 40,000 fatalities a year in the United States.
We have time for one more question, Jimmy.
Yeah, last one. Cecilia asked, is there a similar simulation for cargo movement? Thinking around the last mile small delivery operations. She works for a logistics consulting company and would like to use EVs for last mile routes growing fast in Brazil.
Right. I'll say if you wait, let me just say one thing.
Yeah, please.
A huge opportunity for looking at logistics and people movement together. So let's say we have 11,000 of these vehicles serving people in Ann Arbor, and next thing you know, they're delivering food, delivering groceries, and they're doing last mile delivery from Amazon hubs and other things. So the temporal pattern of goods delivery, a lot of stuff I buy e-commerce doesn't have to be there instantly. Maybe it can come at night when our fleet's less utilized. So I think there's really interesting work to be done in that area. Saif?
Yeah, that was exactly the point I was going to make, is that you could take advantage of these temporal features in vehicle usage, right? When the vehicles are not transporting people at night at 3 a.m., you could leverage them to do other things like delivering packages. Yeah. But there's also an opportunity to do good applications of autonomy is obviously long haul, right? Shipping, so on.
Thanks, guys. Alan, back to you to wrap things up.
Yeah, so I really appreciate this last question because the Electric Vehicle Center has now expanded into drones and the integration of that into cargo delivery for small packages. So I would like to thank our speakers once again for a fascinating vision of the future. And thank everybody for the questions. We didn't get to all of them, but I'm starting the discussion of what's the next phase of this study. And some of these questions are motivating things. Saif we'll need to talk through. I do want to plant one seed so you can think about before we meet. The university is landlocked, and the expansion and building tends to spread us out more, right? Where you want to be able to walk everywhere as the students. I'm imagining a business case for elimination of the parking lots, right? And how that's hindering our ability to locate new buildings adjacent to where the existing ones are. So we may talk about how to build that business case for U of M. So again, virtual applause for a great thing. And if you are not yet a member of an affiliate of the Electric Vehicle Center, please just go to our website and become an affiliate so you get informed about these webinars, our symposium, and other meetings, as well as highlights. So thanks everyone again, and Saif, I'm looking forward to finalizing what phase 2 looks like.
Great. Thanks, Alan.
Thanks, everyone.
Really appreciate your support. Thank you, everyone.
Thank you.
Thank you.